the eye is not a camera. A banana is yellow because it reflects yellow light. Foliage is green because the chlorophyll in the chloroplasts reflect green light. And what our brain actually does is it's not really interested in the absolute amount of green that it can detect. It's really interested in these like relative values. The brain being interested in differences, relative differences in illumination is what allows for us to be able to see things in really bright conditions and then also in really dark conditions.
It's kind of like the brain is constantly making educated guesses about the world. But from a neuroscience perspective, what is color? Have you ever looked at a strawberry and wondered why it's red, even in different lighting conditions? Or why a white shirt, even in the light of a sunset, still looks white, despite the light hitting it completely differently? What if your brain isn't just detecting color, but it's rather correcting, interpreting, and even guessing it? And more strangely, what if the colors you experience don't actually exist in the world at all, but they're rather something that is created by your brain? These questions force us to rethink something that feels completely obvious, that seeing is just about taking in information. But that's not true. Your world might just be a construct and something that your brain has been building. Hello. My name is Avnish, and this is The Early Perspective, a podcast where we explore how the brain works and what that means for how we learn, think, and live. For today's episode, we're going to be diving into one of the most fascinating questions in neuroscience: how we turn light into experience. More specifically, how the brain creates color, how the retina encodes information, and how what we see is shaped not by just the world, but by the computations happening inside of us. To help break all of this down, I'm really excited to welcome today's guest, Deepthi Bannai. Deepthi is a fourth-year neuroscience student at UC Berkeley, working at the Redwood Center for Theoretical Neuroscience, where she explores how the brain works and makes sense of the visual information it encodes in surprisingly efficient ways. She works with Bruno Olshausen and Jacob Yates, and her research blends neuroscience, math, and computation in order to understand how we actually represent the world that we see. At the core of her work is a really powerful idea. The retina isn't just passively capturing images, but it's rather actively transforming and compressing visual information before it ever reaches the brain. Deepthi, thank you so much for joining me here today.
Thank you for having me. Happy to be here.
Of course. Okay, so just to start off, I'd love to go back to the beginning. Can you tell me a bit about your journey into neuroscience and how you actually ended up focusing on vision and perception?
Yeah, it's been a very nonlinear journey. So when I was in undergrad, I studied engineering and chemistry, and I was really interested in I really like solving puzzles. And I was really interested in solving puzzles about the human body. And so I thought I wanted to go to medical school. And so I got my master's in Boston and then very quickly realized that I could not do blood. But I was still really interested in solving puzzles with the human body. And so for our second year for our master's program, we had to do a research year. And so I ended up joining the lab of Materi Keshavan and Paolo Lozano at Beth Israel Deaconess Medical Center. And they were studying the neuroimaging and retinal imaging correlates of psychosis spectrum disorders, so schizophrenia, bipolar disorder. And I was mainly on the retinal imaging side. And so I spent maybe like 3 years there and was really studying a lot of the like structural and vascular differences that people with schizophrenia and bipolar disorder have compared to, a cognitively normal person. And these, kind of differences you also see in various other neuropsychiatric disorders. And so that kind of got the ball rolling of, if the retina is unable to sort of capture or efficiently transmit like visual information, then how is the brain going to be able to construct like a normal percept with bad visual data, or is it in conjunction with misaligned wiring or something in the brain of people with neuropsychiatric disorders. And so that's kind of how I got really interested in this connection between the retina, vision, and perception. And so when I applied to graduate programs, I was really interested in kind of modeling this, and in the sense of like if I can build a model of what a normal kind of visual system might be able to do, we can maybe mimic what we see in various disorders to better understand what might be happening there and maybe hopefully develop better targeted therapies. So that's kind of how I ended up
Yeah.
doing theory work.
Yeah, it's a really fascinating story. How was it transitioning from medical school to something completely different? How was that experience?
It was actually pretty, I think, seamless. Like, I think
Hmm.
when I kind of was honest with myself and said I wanted to do a PhD instead of medical school, I think there was some part of me that was like, yeah, I think
Hmm.
that's the
You
right
just
decision.
understood it,
So
yeah.
yeah, I think so. Yeah.
It's really fascinating, especially how you found your interest in studying vision and how the brain's really encoding information and figuring how bad visual data, as you were saying. So I know that your work focuses on something we experience constantly, but that's rarely questioned. I even had another episode on the retina recently, and that perception in general, and people don't actually question how we are seeing things, they just accept it. So let's just start with exploring that. And something that feels really simple is color. We think of color as just something that objects have, a banana's yellow, stop sign's red. But from a neuroscience perspective, is that really true? What is color in that aspect?
Yes, that's a good question. An object has a specific color because it reflects light of a specific wavelength. Humans are able to see the visible wavelength spectrum. So that's why we see purples and blues and greens and yellows, and oranges and reds. And a banana is yellow because it reflects yellow light. Foliage is green because the chlorophyll in the chloroplasts reflect green light. And what our brain actually does is it's not really interested in the absolute amount of green that it can detect. It's really interested in these like relative values. So in the retina, you have these sensors called photoreceptors, and we have three types of cone photoreceptors, which are capturing color. And they roughly are analogous to like the red kind of region, the green kind of region, and the blue kind of region of visible space. And so when the brain is trying to create a perceptive color, what it's doing is it's using the relative activations of these three cone types. So it's interested in like how much more blue is there than green, or how much more red is there than green, and using those kind of differential values, it creates color as we perceive it.
Is there differences in the way different people perceive color? If, for example, there's variation in those cones as you're talking about?
Yeah, so that's actually what's really interesting. So in terms of normal color perception, you do see like a wide range of ratios between these like red cones and these green cones. And that ratio like varies quite significantly, even though there's no really change in color percept,
Mm-hmm.
which is very interesting. And even in like normal color perception, there might be slight differences in maybe how vivid someone sees a green, or like shades of whatever. Like I like to paint, and so for me I'm like, okay, there's like 15 types of green, whereas my partner might be like, oh, there's only three that I see here. um, but this is more evident in people that have like red green color blindness, so they're not able to distinguish shades of green from shades of red, or people that may have something called tetrachromacy. So this is where they have a fourth cone type. And so the idea is that they see even more vivid colors. But obviously, because people that have three cone types, we don't really know what that perception means. It's really
Mm-hmm.
hard to kind of categorize or kind of even understand what that could look like. Yeah.
What do we know about that fourth cone type? Because you were saying that the three cones are like kind of associated with red, green, and blue, right? So do we understand anything about that fourth cone type?
I think so. I'm not as familiar with the literature, but there are people who study that kind of work, including some folks at UC Berkeley. The idea, I think, is that or at least I guess what I do know about it is I think it might be somewhere around like the green and red,
Mm-hmm.
but I'm not 100%
Yeah,
sure.
it's very interesting. Yeah. And then to look at the other side of variation, there's similarity amongst different situations. And that's kind of mind bending in the fact that the way color is constructed stays almost similar in different lighting conditions. For example, obviously in the morning, it's very bright and you can see everything very clearly, but in the sunset, you're still able to make out what color you're seeing is. So, how's the brain managing to do that? Even being able to identify the same color even under different lighting conditions.
Yeah, it's a good question. So this is the idea of like color constancy, or our ability to be able to perceive object colors as the same under different kinds of lighting. And what the brain does is it uses this kind of like contextual comparison. So it's never really interested in absolutes, or at least like the retina is not trying to encode anything in absolute terms. It's always about relative differences. So, for example, in a scene, if you have low lighting or if you have like really high lighting, what the brain is going to do is, if you have an object, say like an apple, and you have it under some light, it's going to take into account the relative difference in terms of like the amount of light that each thing in the scene is emitting. And so when it's kind of creating this construct of a percept, it's going to estimate and kind of correct for the color of whatever light source it is. So if it's like a blue light or yellow light, outdoor light. And this is something that happens like in the higher kind of visual areas. So it's able to integrate all this kind of information in order to create this sort of stable, constant color perception.
And these essentially it calculating the differences is allowing us to have that color constancy as you're talking about.
Yeah, yeah. The brain being interested in differences, relative differences, and illumination
Yeah.
is what allows for us to be able to see things in really bright conditions and then also in really dark conditions.
Yeah, that's very fascinating. It's kind of like the brain is constantly making educated guesses about the world.
Exactly right. That's kind of what we're doing.
And then I know you also mentioned that information is being encoded from what we see. So, what exactly does that mean in simple terms?
Yeah. So the retina is this like, part of the back of your eye. And this is what's actually like capturing light information. And what it does is it converts it into electrical signals that the brain can use in order to create perception. And uh, the one kind of thing that it has to deal with is, your eyes right here and your brain, like the visual areas are kind of back there.
Mm-hmm.
And so that signal has to travel quite a distance. And it travels through something called the optic nerve. And unfortunately, the optic nerve is kind of like a bottleneck. It can only send so much information. And so what the retina has to do essentially is take all of these, visual signals that have a really kind of high dynamic range and then compress it into something that's much easier for the brain to kind of understand. And because of this kind of like bottleneck, it needs to really, really compress it. And so the idea of encoding is really just taking information about visual, scenes, and then converting it one into code that the brain can use to create perception, but also doing it in a way that is efficient and compressing.
Mm-hmm. And then if it is being compressed, how is it making sure that the information is accurate? Like if you think about it like a computer compressing a file, some information is lost and then that might make, for example, if you're compressing a video, the video becomes bad quality, right? So how do you keep that information accurate? What is the brain doing there?
So this is kind of where like prior knowledge comes into play. So in neuroscience, we like to say that perception is an inference. So it's not necessarily like an objective truth about the way that the world is. It's a construct that's made both from senses that you measure or perceive, as well as, prior assumptions that your brain has. And so in some sense, we are kind of hardwired to have some prior assumptions about how the world works. So, for example, uh, in motion, at least in the natural world, depending on where you are, there can be, like pretty low motion, unless it's like windy or something. And so the retina part of it, one of the things that it's really interested in or like really looks for is like motion in general. So anything like high motion, it's kind of like, oh, something's there, and that's what I'm going to encode. Um, so it's not necessarily that there's a way to know that perception is accurate. It's really just using prior assumptions, and then as you grow up or like learn more about the world, you can your brain gets to integrate that as well. So it's a little bit of hardwired biology, a little bit of the world itself, and then
Mm-hmm.
a lot of it is kind of experiential as well.
Mm-hmm. Yeah. So if it is based on prior assumptions so much, is there differences between age groups seeing something? Because of course, the older you get, the more life experience and the more visual experience you would have.
That's a good question. I'm actually not really sure how to answer that, because there's such a wide difference as well in the kind of ability of components of like your eye, your retina, your brain to be
Mm-hmm.
able to construct perception. So I'm not sure that I can answer that question.
Mm-hmm. Yeah.
Yeah.
I mean, of course, I'm sure even testing this kind of question in the lab would be hard. There's so many things you can't control, as you were talking about, even with aging. I'm guessing your visual ability would also go down. So then there's too many factors, I'm guessing.
There are, but I think there's ways that you can control it. I think it's a really good question. I'm sure,
Mm-hmm.
someone's kind of looked at it and studied it, but I unfortunately don't know that information.
And then since we're talking about simplifying information, what exactly is prioritized and what is being removed and filtered out?
Yeah. So, like I said, the brain and the retina, at least like visually, they're interested in differences, or at least I guess the retina is.
Mm-hmm.
And so, things like if we take, say, you're looking at a landscape, like say there's a mountain, there's some trees, some sky. What it's going to prioritize is unique object or like unique features. So things like edges, things like contrast. Um, and it's going to deprioritize things that are very uniform. So, like the sky. If you look at two kind of regions of the sky, they're going to be pretty similar. Um,
Mm-hmm.
whereas if you look at, say, two regions of a, mountainscape, it could just be seeing mountain in one area or tree in another area. So, what it's doing is something we call redundancy reduction. So, it's trying to take the kind of key features of a scene, so like edges, contrast, and take allow for coding to be used there. So like it'll use energy on that to encode that. Whereas things that are a little bit more uniform, say like sky, patch of grass, it's going to kind of compress a little bit more.
So you're saying even different environments kind of choose the information being processed. If something's more redundant, as you're saying, it'll be filtered out more.
Yeah, I would say that's a good way to put it.
And then if the optic nerve, as you're talking about, has a capacity, what does it do when there's a lot of visual information and visual overload?
Hmm. I think that might be more of a processing question for the brain. So it's not like it. I'm not an optic nerve researcher, but from what I understand, it's really more kind of like an information pathway. So it really
Right.
just kind of gates the number of, I guess, signals that the retina can send to the brain. Um,
Mm-hmm.
and from, obviously there's some work that probably shows that it has some processing capabilities, but at least for the kind of research that I do, I think of it more as
Mm-hmm.
like a bottleneck, just kind of restricting the amount of messages that the retina can send.
Right. Okay. And then since we're talking about your research, could you tell me a little bit more about your research specifically?
Yeah, sure. So I'm interested in this idea of efficient coding in the retina, so some of the topics that we talked about.
Mm-hmm.
And the overarching kind of hypothesis of efficient coding suggests that the brain is encoding sensory inputs in order to maximize information capture and transmission while minimizing energy usage. So things like, neuron amount, just general metabolic energy. And so this is the idea that like the nervous system is using its limited resources wisely. Um,
Right.
and so my interest is kind of on the front end side. So I'm interested in understanding how the retina is able to take such a wide dynamic range of sensory information and compress it down into a very smaller dynamic range of neural coding. And so one of my projects is focused on understanding the makeup of the cone photoreceptor mosaic. So these red, green, and blue cones. They are, as I said, varied in some individuals, but we don't actually have that many blue cones. They're quite sparse, as we say. And that's particular in like the fovea, so this central region of high acuity vision. And so what the retina is doing essentially is it's prioritizing these red and green cones over the blue cones in this region of high acuity. And so one of my projects is working on trying to mathematically understand and model why that's the case.
Mm-hmm. So why does efficient coding matter for the brain? What are the benefits of it?
So so the framework essentially is a way to think about why certain mechanisms or circuits exist within the retina or the brain. And one reason for why the brain would want to do efficient coding is just that it would be able to efficiently, dish out resources to different areas. And so that way it's not actually trying to encode everything or take in everything. What it's doing is it's taking in information and processing information that's relevant to an organism's survival. So things like behavior, social behavior, it's all in like relative context. So generally, things that aren't really useful for that, the brain is going to say it's actually not really useful for me
Mm-hmm.
to
Yeah.
use my limited resources on things like that. So
Okay. And then are there any trade-offs of doing efficient coding?
the biggest trade-off really is that you're not going to be able to capture everything. So you lose fine-grained detail. So for us, we can't really see, there's like a limit to how well we can see at a certain distance, or like at nighttime, right? We can't really see as well, and we don't really see color as well. Unless we have like some kind of illumination. Whereas other animals, especially animals that are more active during the nighttime, um, they will their systems will prioritize like maybe nighttime vision, or maybe they don't actually care about distance vision. Um, and so it's always going to be a trade-off between what information about the world are you interested in order to survive. And so what that means is, we can see really well, but dogs can't really see that well with color.
Yeah.
So it's always like a relative trade off.
So primarily this has been an evolutionary advantage, and then that's diversified in species.
Yeah, I would say so. Yeah. And it's really, I think, one of my favorite rabbit holes during my PhD has been looking at like just like reading and understanding about the differences and different animal vision, and kind of,
Right.
it's fun to kind of characterize like what exactly is going
Mm-hmm.
on in that system based on like what that animal is doing or what its kind of niche is.
So, how exactly are you able to study these? Like, what methods are you using? Because it seems like studying such efficient coding in the brain seems quite complicated. So, what tools are you able to do it with?
Yeah, so it's a lot of math. It's like theory work, it's computational work. So part of it is using mathematical tools in order to describe a process by which like a system would want to say maximize transmission of information of some type. So say like color information. Um, or it would be math in being able to build these kind of statistical models that I can train using data. So it's and then also I need to know a lot about biology, like what kind of assumptions do I need to bake into my model? What kind of restrictions and limitations do I need to take into account? So it's a really fun kind of way to have my fingers in different little pies. I want to say, but it's also kind of you get stretched in different directions. I feel like some days I'm really learning some new kind of algebra, and then other days I'm like sitting at my computer wondering why my code is not running. Um, and then there's some really nice days where I get to just read papers and learn more about how cool biology is. Um, so yeah, there's a lot of different things that kind of go into this line of work.
Yeah, for sure. That sounds very, very fun in the good days.
Yeah.
So what restrictions do you actually assume? Like you talked about the restrictions you have to take into account. So what exactly are those?
So one would be like I'm interested in primate or human vision, and so we only have three cone types, so I only allow my model to have three cone types. Another one is when so the front of the eye, so like your cornea, lens, your pupil, what they're going to do is they kind of filter some of that visual information. And so some of that is kind of baked into my model as well. So how exactly does that happen? It turns out there's the kind of these optical properties of the eye are really attenuating or reducing the amount of kind of information in this blue channel that we have. And that's kind of related to why you have fewer blue cones in your eye. And so those are kind of the things that I like have to like bake in because I want it to be as biologically plausible as possible.
So does your work primarily apply to humans, or is it also uh are you also focusing on other animals?
For now, it's just humans, but we are able to model other animals like mice
Mm-hmm.
or tree shrews. I'm really in, or like other non human primates, so macaques
Mm-hmm.
and marmosets, animals that are from a similar evolutionary line, but have slight differences in terms of the machinery or circuits in vision. And I'm really hoping that I can get some like interesting, be able to do some interesting animals, like say underwater species or something like that. Um,
Right.
but yeah,
Yeah.
but it can be extended. For now, it's not, but I would
Okay.
like to think I
Yeah.
could. Yeah.
Perhaps in the future. Yeah.
Well, yeah, we'll see.
Okay, I just want to pivot for a
Mhm.
quick bit. So
Sure.
I want to talk about the limits of human vision. Of course, we do have a lot of limits, but how is the brain able to fill gaps of things that we can't see? Of course, we talked about the inferences it's making and the many of the previous experiences it's using. But then, what about the different gaps that come about?
Yeah. So I think the first thing that comes into mind is something like contour completion. So this is the idea of like, if I have my like hand here and there's like maybe something blocking it, I know that like my hand is continuing. So there's some assumptions about, the fact that objects continue. That would be like a very simple kind of prior assumption that the brain might use to be like, no, Deepthi's hand's not just like cut off randomly. There's like an object that's blocking it.
Yeah.
Another one that I think is really fun is with eye movements. So
Mm,
even when you hold your eyes still, your eye is doing these very tiny movements. And then as you look across a scene, your eyes kind of jumping around.
mm-hmm,
And we don't really experience that jumping around. So what the brain is doing, people hypothesize, is it's sort of doing this filling in between
mm-hmm.
our eyes, whatever region our eyes kind of swipe between, in order to, I think, thankfully, have a kind of stable perception of the world
Yeah.
instead of one that's kind of like, oh, moving around and kind of blurry.
Yeah, I know. I actually completely understand the eye movement. I think many videos online have been popular with people like showing how their eyes moving like crazy when they just look around. So yeah,
Yeah.
it's very fascinating.
Yeah, no, it's very cool. It's very cool about the stuff that we just don't
Yeah.
perceive ourselves doing. Yeah.
hmm Yeah. And then another thing is, of course, technology is trying to emulate the human body and the human eye. But how has it been so almost impossible to replicate it? Because, of course, we've copied many of the aspects like RGB, like the cones and the stabilization and a lot of the inferences. But then what has led to such a big gap forming still and remaining?
That's a great question. And I think I might lecture you for a little bit, so I apologize ahead of time.
No
Um,
problem.
so from the beginning, right, it's kind of been this like monumental process where we uncover more and more things that we just don't know. And so, I work on the retina
Yeah.
mostly. I'm in like, a little 8 layer piece of tissue at the back of the eye. And then there's things in the brain that are much more complicated that other people
hmm
are, working on. Um, so this idea of like being able to fully solve vision, I think is luckily, hopefully not going to happen anytime soon. Otherwise, I'd be out of a job, myself and a lot of other people. But there's a
hmm
lot of things that we do understand and things that we are uncovering. And especially with, these kind of like deep learning, artificial neural net tools, those things have been really great in being able to process a bunch of data and help us get some more understanding of just the things that the retina and the brain do in order to encode and give us visual perception. I might have lost your question there a little bit, but you were talking about like emulated or
Yeah.
embodied
I mean,
visual
that is
systems.
essentially the philosophy that many like tech pieces of technology use. They're trying to copy the eye, but then of course they're failing in at least as of current times. So I was wondering why that's so hard to copy.
Yeah, I mean, I think one thing I can give you one example. So
hmm
Um, something that people you might notice with say like your phone camera is that, especially for me, if it's like nighttime and I'm trying to take a nice photo of the moon,
hmm
I can never just get it right. Like it always just kind of
Yeah.
looks wrong. And then I look at it like with my eyes and I'm like, no, no, there's like so much more detail. Why are you not capturing
Exactly.
this? Um, and this like fundamentally just comes down to the fact that like um, the processes that are the biology has kind of evolved to do over millions and millions of years
hmm
involve a lot of like nonlinear kind of complex adaptations, and so we just have not uncovered what really those are, and so we can emulate what we know, but I think it's kind of in a way it's like poetic and a little beautiful to be like, okay, there's a lot that we really can't do, and so until my phone camera is able to take a photo that's as good as me, my own eyes just like seeing something, I think that we still have some ways to go, but there's a lot that we can you know learn from biology in that sense,
hmm
not just with like phone cameras, but like screens and digital displays, right?
What do we actually still not understand, especially in terms of technology or implementing it? Because I know you were talking about the fact that uh, in that conference they discovered that there's so much they don't know that it's almost like impossible to find out in just one sitting. But then, what do we still not know, despite it being what almost over 70 years, right?
So, for example, I think one thing would be with, say, like your phone display or like your camera, your any kind of display. Within each kind of like unit, so like pixel, there are three color sensors. So you have a red, green, and blue.
Yeah.
And so what it allows for us to really see are like these like really nice kind of images on our screens, and it's great. Uh, but what we actually have in biology is like each kind of pixel, one could say, in the retina is only one of those three, at least in humans and most
Right.
kind of mammalian species. um, and so there's probably some kind of clever uh, machinery that's behind why we can do this in a really efficient way, because you could probably save a lot of money. I don't know, by
Yeah.
not having to use, 3 different kind of sensors. So that's like one kind of simple
Hmm.
way, one kind of simple thing that we still don't really
Right.
um, fully understand, like how does it go to uh, color perception. But there's obviously, a lot more um, that I could get into, but
Yeah.
that's one simple one.
Hmm. And then since we're already on the topic of the applications of your research and just research on color perception and sensory encoding, how else does understanding this actually matter and benefit us?
Yeah, it's a good question. So there's obviously, I think, the healthcare aspect of it, which I'm interested in. So if we can understand, say, like what happens in terms of like color processing in the retina, we could help people that have disorders that mess with like the cone photoreceptors or the rods, so they're not actually able to, collect visual information. But what we could do is potentially design and build a prosthetic implant that can be put in the eye that allows for some of that collection or processing. Um, so that's one. Another would be, we can just advance technology in general. So the kind of, artificial neural net explosion, I would say, at least like convolutional neural nets, like all of that kind of came from visual neuroscience in a sense.
Right.
And it was a very kind of simple um, way of modeling, what they saw in the visual system doing. And we got
Hmm.
a lot of utility from that. And we know that there's a lot more complex things that it does. And so if we're able to maybe uncover that and apply it, we could get better and better technology. And then there's obviously the kind of like scientific pursuit of like, it's really nice to be
Yeah.
able to understand and like, know what biology is doing,
Right.
and how it's like evolved over the years, and maybe get like, if you're a philosophical person, like a better understanding of the way
Yeah.
of the universe and how it's built. So there's a range of
Yeah.
reasons for why.
Very
Yeah,
useful research.
I think so. Yeah.
Okay, so I just want to do a rapid fire round before we end off here today. I'm just gonna ask a series of questions. I just want you to answer as quick as you can and as, I don't know, as concise as the answer can be.
Sure.
Okay?
Okay.
Okay, so let's start off then. What do you think is the biggest misconception that people have about vision that your research challenges?
Oh, that's easy. That the eye is a camera. The eye is not a camera. It's not just statically capturing frames, it's an active sensor. The way I like to explain it is it's kind of like a fingertip, kind
Hmm.
of touching around a textured object, trying to understand what it is. That's what your eye is
Yeah.
doing to a scene. It's not a camera.
Hmm. Okay, so then what's something about the retina that you were surprised to learn about when you first discovered it?
How complicated it is. It's a very small layer of tissue. It for my thoughts, I was like, oh, it should be pretty straightforward and pretty easy. But there's so many different kinds of cells. There's so much complicated machinery. It's astounding to me how complicated just the front end is.
Hmm. Then the next question would be, what is the biggest unanswered question in visual neuroscience right now, or some of the biggest?
Oh my gosh. I would say one of the biggest questions is really just how does perception happen? And you could break that question down into multiple things, like how is this information encoded? So, some of the work that I do, some of the people that I work with are really interested in, okay, so what do different regions of the brain do? We don't fully understand what,
Right.
the visual areas of the brain are doing. And then there's obviously the question of like, how the heck does it get integrated? How do you put all this stuff together to create what we see?
Yeah.
So I would say, there's a lot of unanswered questions, luckily.
Hmm. Yeah. Okay. And then if somebody listening wants to go into research like yourself, what would you say is the best piece of advice to if they want to go into neuroscience or computational research?
Yeah, that's a good question. I would say, something that I learned on my way to getting a PhD is that progress is very nonlinear. You don't have to
Mm-hmm.
know what you're going to do next. And I think the moment I kind of realized and learned that, my life got a little bit better. I kind of chased what I was interested in. I am not I did not come into grad school thinking I would do computational neuroscience or
Mm-hmm.
theory. But I had an advisor, or I have an advisor who like really believed in me. And so I would say, one, you kind of have to believe in yourself, and two, it like really does take a village. And
Yeah.
it's not going to just happen in the first go. It might take a couple, but
Mm-hmm.
if you're passionate and interested, I think that opens a lot of doors.
Mm-hmm. Okay, last question. If somebody listening could only remember one thing from this entire episode, what would you want them to understand about perception?
My one thing would probably be that there's no objective, like, truth for how
Mm-hmm.
perception is. There's no one way to perceive. Everyone perceives things differently. And that difference comes from our biology, so how our body and brain is made up, and also from the way that we have assumptions, whether it's genetically hardwired or things that we learn through experience. So perception is subjective, it varies between people. And I think that's a very important lesson to keep in mind.
Mm-hmm. And it's also very important to respect that difference amongst people. Mm-hmm.
Absolutely. Yeah.
Yeah. Okay, Deepthi, thank you so much for joining me today and helping make such a complex topic feel intuitive and exciting. What I loved about this was especially how it reshaped something that we take for granted. Of course, vision, we never think about it, but it's so interesting and complex, especially the processing that happens even as we're talking and looking at each other right now.
Yeah, absolutely. It's a beautifully
Hmm.
complex and kind of frustrating sometimes process, but
Yeah.
yeah.
Yeah, it's about making the predictions, the compressing information, constructing a version of reality that's useful, but of course not perfect. For listeners, if this episode made you rethink how you see the world, literally, share it with somebody you think would find it interesting. If you guys enjoyed this episode and learned something new, make sure to follow on your favorite podcasting platform or on YouTube. I'm Avnish, this is The Early Perspective, and I'll see you in the next episode.